Welcome to this new video. Here is an example of orthogonal diagonalizations of matrices. Okay, so as we saw from the previous video, to show that the matrix A is orthogonal diagonalizable, we have basically three steps. Okay, the first step here is to find the eigenvalue associated to this matrix A. Second step is to find the eigenvector associated to each eigenvalue. And the last step is to find the matrix Q, the orthogonal matrix Q, and the diagonal matrix D. All right. So once we understand that, let's start. What is the eigenvalue associated to this matrix A? I know from the previous video we show you how to find the eigenvalue. It should be easy to do that. So I'll just provide the eigenvalue so that we can continue with the calculation. First step, eigenvalue. Eigenvalue. Well, in this case we have lambda 1 is equal 8. The second lambda is also 8. So we have double here, double eigenvalue, and lambda 2 or 3, if you want to call it like that, is 11. Okay, so please double check this and make sure that you obtain 8, 8, and 11. Right, once we have this, let's move to the second step, which is the eigenvector. Eigenvector. So we want to find the eigenvector associated to the eigenvalue 8 and 11. So first step, we start with 8. Eigenvalue problem. A minus lambda I, let's say lambda 1 times x vectors is equal 0 vector. If we substitute these, what do we have? We have 9 minus 8 is 1. The second one is 1. 9 minus 8 is also 1. 1. All this multiply x1, x2, x3. This is 0 vector. All right, you can solve this and you obtain x1 plus x2 plus x3 is equal 0. If we fix the value of x1 and solve for this, this is x2 minus x3. And from here, the eigenvalue associated to this one is A8. So when x is, this is alpha times minus 1 coming from this, right? Minus 1, 1 and 0. The second one is minus 1. This is plus beta. I say plus beta, minus 1, 0 and 1. Of course, alpha and beta are real, and they are also non-zero, right? All right. We have this, the eigenvector for the first eigenvalue. Let's look for the eigenvectors for the second eigenvalue. So for lambda equal lambda 2, we have 11. So same eigenvalue problem. 9 minus 11, this is minus 2. 1 minus 2, 1 minus 2. So this is x1, x2, and x3, all equal 0. All right, if you multiply this, you have minus 2x1 plus x2 plus x3 is equal 0. So here, this is a vector, eigenvector is gamma 1, 1, 1. Solve this, okay, with gamma in a real and also different from 0. All right, this is what we have. What's the next step? You have the eigenvalue, the eigenvector. For the third step, we want to find the matrix Q and D such that D is equal Q inverse AQ. So the matrix D is straightforward because it's just a diagonal matrix, okay? And Q is an orthogonal matrix. Remember that the orthogonal matrix, we generally use the vector sets coming from the eigenvectors. So if we call these guys V1, V2, and V3, then orthogonal matrix Q should be a vector, it should be a matrix made of these vectors, but under a certain condition. You should make sure that the norm of these vectors, so norm of each vector, to find this we have two steps. The first step is the following. We have to make sure that the vectors are orthogonal. They are mutually orthogonal. What does that mean? V1, V2 should be 0, as well as V1, V3 should be 0, as well as V2 and V3. The inner products of these vectors should be 0. That's what is meant here by being mutually orthogonal. The second thing here is the norm of each vector should be 1. So the norm of V1 should be 1, the norm of V2 should be 1, and the norm of V3 should also be 1. Alright, let's then check if V1, V2, and V3 are orthogonal as we start with the first criteria. If you look at this V1 and V2, the cross product of V1, V2 is V1, V2 is 1. Unfortunately, it's not 0. The cross product of V1, V3 is 0. And the cross product of V2, V3 is also 0. Alright, once we know this, it is tricky, but it's not the end of the world because we have to deal with this one. I want to decompose this vector. I can choose to do the V1 or V2, but let's start with V1, okay? I want to decompose the vector V2. Let's take this as our vector V2. This is V2, and V1 is somewhere here, something like this. Here is V1. So I want to decompose V2 in two vectors called U1. Let's call this U1, and this is U2, okay? So V2 is equal U1 plus U2. All right, from this graph, U1 is parallel to V1, and U2 is orthogonal to U1, or you can just say U2 is orthogonal to V1. So this also means that U2, V1 is equal 0. And here, given that U1 is parallel to V1, so this is U1 is equal X times V1. All right, let's substitute here and see. So V2 become X times V1 plus U2. All right, at this stage, I decide to multiply the whole thing by V1. So let's multiply here by V1, here by V1, and here as well by V1. We know that U2 and V1s are orthogonal. It means that this product will be 0, and we only remain with this, okay? And from this product, we can solve for X. X become V2 times V1 divided by V1 times V1. So if we take the products of V2 times V1, this is minus 1 times minus 1 is 1, 0, 0. So this is 1 over V1 is 1 plus 1, this is 2. All right, we know that U1 is equal X V1, this is half of V1. V1 is minus 1, 1, 0. Let's solve for U2. U2 is, from this equation, U2 is just V2. U2 is equal V2 minus U1. Minus 1, 0, 1. Minus, this is minus half, half, and 0. All right. If we subtract this, minus half, this minus this is minus half, and the last one is 1. So I don't want to deal with fraction. I choose to write 1 over 2 bracket minus 1 minus 1, 2. Okay, we have decomposed the vector V2 into V1, into U1 and U2. So we now have a set of 3 mutually orthogonal eigenvectors. So the set is V1, 2 U2, and here is V3. Okay, 2 U2 because as you saw here, I not dealing with this, so this is what I call U2. That's why I have to put the 2 here. So we have minus 1, 1, 0. The second one is minus 1, minus 1, 2. And the last one is 1, 1, 1. Now we have completed this first step. Let's look at the second step, the norm of each of them. The norm of this vector is not 1. The norm of the second vector is not 1, and the norm of the third vector is not also 1. We have to scale these vectors in the following way. We have to choose S to be, the scale vectors is minus 1 over root 2, 1 over root 2, and 0, minus 1 over root 6, minus 1 over root 6, 2 over root 6. And the last one is 1 over root 3, 1 over root 3, and 1 over root 3. Finally, the matrix Q, let me write it like this, is minus 1 over root 2, 1 over root 2, 0, minus 1 over root 6, minus 1 over root 6, and 2 over root 6. And the last one is 1 over root 3, 1 over root 3, and 1 over root 3. So we know we have the matrix, the orthogonal matrix Q, and the diagonal matrix is 8. So it should be eigenvalue corresponding to the first eigenvector, 0, 0, 0, 8 for the second vector, eigenvalue corresponding, and the last one is 11. So this is the matrix D. All right, we have decomposed the matrix. We have the orthogonal matrix Q, and we have a diagonal matrix D. So as assignment, I'll ask you to double check this. Verify that D is equal Q inverse or Q transpose A times Q. This is similar to Q transpose A Q. This is what I want you to verify, okay? This is your assignment. You should be able to verify this. It's just a matter of multiplications of matrices. All right, this is all for this example. I hope you were able to follow me. So see you in the tutorial.